And the final week, I'm going to give you an easy quiz. An easy quiz one where the questions repeat and you get full marks for getting 50 for being right on 50% of the questions. Right? I mean, I have to give you a break at some point. Right? So I am going to see you guys 3 more times, and I'll miss you. Right. Any questions about any of the topics we've covered so far? Okay. Has the recording begun? Yes, it has, right? So any questions about any of the topics we've covered so far? No. Today's
पूछ लेगा.
Okay.
okay. Great. It's like this. If you've got full marks so far, you don't need to worry about the quizzes. Also, attendance. You're required to attend 20 lectures out of 27. If you've already done so, if you don't attend one more lecture, you're not going to get penalized. You will be fine. So, are we going to come up any moment? Exciting times. This room has been, one big technology bug since the beginning of the semester, and it looks like it's going to stay that way till the end, right? What's happening?
Not sharing here.
Is it sharing on the other screen by any chance?
No, it's off.
Something happened. Yes. So, folks on Zoom, can you see the slides?
Yes.
I think I heard yes. All right, let's begin. It's slightly late. So, we're going to continue our discussion on generative models. By generative models, I mean models that can generate data, that can learn to generate data of specific types. So, we've looked at these were the final topics of towards the end of the semester. We've seen VAEs as generative models. We're going to look at GANs. And in the week after next, we're going to be looking at Boltzmann machines, which are also generative models, but it's slightly different. So here's the problem. You're given a large collection of data, maybe images of faces. You want to train a neural network to generate more data of the same kind. So this is a problem of generation. Now, whenever we have a problem of this kind, the underlying problem that we're really discussing, remember, we want to generate new novel faces. You don't want to be reconstructing something that you've already seen. So you want to see maybe 1,000 or 1,000,000 faces, but then the new face that you draw must be something that has never been imagined before by anybody except your neural network. So from a distribution perspective, what this means is that you want to learn the distribution of the class of data, and then you want to be able to randomly sample from this distribution. So what we really want is to learn a generative model for the data. And so here is a key distinction between generative models and discriminative models. When we're speaking of classification, we have always been asking this question. Here are some data. What is the class? Here are some audio. What is the phoneme? Here are some pixels. Is this a picture of a flower? So now it's the task is one of discrimination. So it's useful to think of everything in terms of two variables. One is X, which are the features you're giving, and Y is the label that you assign to the class. The label could be discrete, it could be continuous, it can be anything, but it's a label that you assign to the class. And we've seen this before. When I use a softmax layer particularly, if I provide some input, what the network is actually computing is P of Y given X, meaning here is some data. What is the probability that this represents a phoneme O? What is the probability that this represents a phoneme E? So you're going to get a probability for each class given the data. And then when you're asked to, if you're required to make a selection, if you're required to perform classification, you're going to select, which one would you select? The most likely class, right? So this is a discriminative model. It tries to, the model actually learns to compute the conditional probability P of Y given X. We've been speaking about this from lecture 3, right? In the case of generative models, this is not what you want to compute. You want to actually say, what is the joint probability of Y and X? Now, this is a much tougher problem. Why is this tougher? Can someone tell me? Why would this be a tougher problem? Yeah. That's the easy bet, right? There's something about X. What is the nature of X in your real typical problem? High dimensional, and it's generally continuous value. It's generally high dimensional, right? So if I were to write this down, I could be looking at simple two-class problem. You know, is this a dog or is it a cat? Y is small, but then X is going to be the set of pixels for the image or whatever features that you extracted from it. So this I can write as P of Y times P of X given Y. What is the distribution of all data that belong to this specific class? And then if you're looking at some high dimensional space, this distribution can be anything. If I were to give it a shape, if I were to draw a level set for this distribution, you might find that the distribution is, you know, a bunch of disconnected things with some kind of peculiar. How do you even? Is that better? This is horrible. Can you? Thank you. Okay. So the problem here is you need some functional form to characterize these distributions. Now, are you guys familiar with probability for functional forms of probability distributions? I'm sure you are. Can someone give me an example? A Gaussian, right? Something else. A Poisson, right? Laplacians, but even more complicated things like hidden Markov models. They're actually probability distributions, right? The thing is, in each case, you have a nice functional form that you can fit, but those functional forms, the number of different kinds of distributions that those functional forms can represent is very, very small. In the class of all possible distributions, the number of distributions that you can actually represent with a nice little formula with a nice bunch of parameters is small. And the odds that whatever data you're trying to generate has a distribution that forms one of these shapes are practically zero, right? So we have this problem over here. So what does the discriminative model do? Because you're looking at P of Y given X, it's learning the decision boundary between classes. I have some data, is it a dog or is it a cat? Where in the data space do I draw the boundary between cats and dogs? That is the boundary that the discriminative model learns. The generative model actually learns the entire distribution. This is this is what makes it much more complicated, because in the process, it has to learn this guy, or alternately, it has to learn P of X and P of Y given X. Regardless of how you look at it, this may be easy to model. It's not really, but this is going to be much easier to model than this guy, right? So it learns the actual distribution of the data, which are very, very hard to characterize. And so now the discriminative model, they are relatively easier to deal with. We spent most of the semester learning discriminative models, but they are limited in scope. There's only so much you can do with a discriminative model. You can perform classification, you can perform a little bit of regression, but you can, if you want to have a generative model, the nice thing about generative models is that if I have P of y given x, from this, I can compute P of x, I can compute P of y, I can compute P of y given x. So this one, if fully known, is sufficient to compute this probability distribution, which means that my generative model can be used to perform classification, whereas the discriminative model cannot. So most of your classifiers, statistical classifiers or Bayesian classifiers, or pretty much any classification task traditionally used to be performed using generative models simply because they are so much more versatile, but then you always had this restriction that there are only so many different kinds of models you can learn. The problem here is, as I said, the distribution can be anything. So you need to be able to characterize this distribution. And we find that more often than not, whatever model you apply to it, to your data, is not fully appropriate to your data. You got, right? So this is the problem that we've been looking at for the past couple of classes. Now, in the case of VAEs, how did we deal with the problem that the data could have this really ugly distribution? Anybody remember? This is a level set. The distribution is a function, right? So how did we deal with the fact that we are only able to characterize such a small number of, a relatively small number of distributions which have nice functional forms, whereas the data can be something ugly, right? So how did we deal with this dichotomy that what we are capable of handling and what we want to model are entirely different? Approximate what? Give me a second. I can't. All right. Can you repeat that? So what was that? What was that approximation? Were we approximating the distribution? We were approximating that. What was that actually used for generation? That was your encoder, right? So how did we actually model it? Anybody remember? Yes. So it was something called a reparametrization trick. Okay. What is a reparametrization trick? You start off with a distribution that you can handle. The specific distribution that we used was Gaussians, but it could have been anything else. And so then you started off with a Z, which had a nice Gaussian distribution, and then you put the Z through some function, which I'm calling D over here, such that this distribution got distorted. The function D distributed this Gaussian to look like the distribution that you really wanted to model. And the entire problem was one of trying to learn this function. And once you learn this function, if you wanted to generate new data from the source, then all you had to do was to draw something from this distribution and push it through the function, right? And characterizing things in this manner made things easy. But that was how we dealt with the problem, that it's really hard for us to characterize these ugly distributions. So we reparameterize. We work with what we are capable of working with, these nice simple distributions like that, and then learn a function that's going to distort it to whatever we want it to be, right? So there's another kind of distinction people like to make. The distinction between explicit distribution models and implicit distribution models. An explicit distribution model, a Gaussian, has a functional form, right? So if a Gaussian has a functional form, it's very easy for you to specify the parameters. You know what the parameters mean. You're able to write a formula for it. And then if I give you an X, you can actually compute the probability for that X using the Gaussian, right? Now, suppose in this case, after having generated X, can you actually tell me what the probability of that X was using this distribution? Can you tell me? It's not possible, right? Why is it not possible? If I work out the formula for this, we actually had some knots out here that we added, right? So we know that P of X given Z was just the distribution of this noise, right? This is something that we could characterize. We saw this was a Gaussian. Everything here is Gaussian. The only thing that's ugly is the function in between, right? Then we wanted to have integrate this and dz. The problem is when you look at the joint probability of x and z, this integral will actually end up being intractable. There's this ugly function d in between, right? Because this is not x, this is actually d of z, right? And this d is a very ugly function, right? So actually it's going to be p of x given z. Let me write this. All right, so when we do this, if we write this p of x of z, that Gaussian with x, but the mean was an ugly function d of z, and this d being as ugly as it is, if you plug the formula for this Gaussian with d of z in the mean out here, and then plug in the Gaussian for z over here and try to work out this integral, you're not going to come up with anything that you can actually work with, which means that if I ask you, this is p of x, right? If I give you any specific x and ask you what the formula is, you will not be able to compute the formula. On the other hand, if I ask you to generate new samples of x, it's easy enough for you to do so. You can just draw z, put it through your function, and draw and compute a sample of x. So do you see the distinction between the two cases over here? In one cases, I have a nice formula, a Gaussian formula. I plug in the x, it will give me the probability. In the other case, the formula is not just not so nice, it's not practicable. There's no way for me to just plug in an x and compute this value. Nonetheless, I can actually generate data from this distribution, right? So this is another distinction that we like to make. So going back to our problem, from a large collection of data, we want to learn a distribution, and the distribution can be horrendously ugly, and we want to be able to sample data from this distribution. So the trick we're going to continue to use is what we did with VAEs. We are going to reparameterize. So this is what we have seen so far, right? We call it the decoder, but it's really a generator. I had an X. The generator. It's a little bit of a misnomer. The generator is the combination of the sampling from the random variable z and passing it through the decoder. But I'm just going to call that the generator using standard terminology. And so this is what we did. We used this reparameterization trick. I drew some sample z. I passed it through this function, out popped some data. And if I learned it properly, then this distribution was known, right? So the way we did it, how did we train the data? Train our function, the function d. So here's what we did. If I'm given a lot of data, training data x, we use the maximum likelihood principle. So does anybody remember what the maximum likelihood principle was? Yes, but how did we specify what fit meant? Anybody else? Somebody? Maximizing? We chose the parameters that made the data most probable, right? We use the world as a boring place principle. And the world as a boring place principle says that whatever you're seeing, it's very typical of your process. So you're going to choose the process for which these data are most typical. In other words, most likely, right? So for any specific setting of my parameter d, so d has some parameter theta, right? So for any specific setting of theta, I'm going to get a different distribution. As I vary the theta, the distribution is going to change. And of all the distributions that you got, you pick the distribution that assigned the highest probability to the data that you're trying to learn the distribution from. Now, the real problem is, as we said, this thing is not characterizable, right? Because this is not characterizable, how do you compute this probability? Computing the probability was not an easy thing. And so we went through this entire rigmarole where we actually tried to go back from X to Z, then we sampled stuff from it. We were computing probabilities of samples drawn from a distribution. You were trying to maximize the probability of specific samples drawn from a distribution rather than, and it gave us a fairly complicated looking process, which in the end all worked out to some nice tidy formula, but the process end to end was kind of difficult to comprehend, right? We can do it differently. So the problem is in the process of maximizing the likelihood of the data, the criterion that we are using to learn the model, which is the probability of the data, has nothing to do with the underlying data itself, right? This is some abstract criterion. I'm trying to learn some function, and I say, find me the function such that the probabilities of these face images that I've seen are maximized. But this doesn't tell me anything about what probabilities it will assign to other data, right? There is no explicit, so there's absolutely no way for you to say that it doesn't assign a very high probability, because the function can be arbitrarily complex, right? And so we know that neural networks are universal approximators. So here's what I could do. I could end up with a probability distribution which just assigns very high probability to the specific training instances that I've provided, and elsewhere it is garbage. We don't have any direct way of controlling the other stuff that you could generate, things that are not part of the training data, and say these two must look like faces. So what we are working on over there is hope that if I make the faces more probable, then when I randomly sample other things from this distribution, those two will look like faces. You're working on an assumption, right? Can we make this training criterion more direct? That's where generative adversarial networks come in. So generative adversarial networks, the word itself has three components: generative, because clearly we are speaking of generative models. We're trying to learn models that can generate data. But the second one is what makes it most interesting. The second one, unlike VAEs, which focus on what happens out here, the adversarial component also tries to address what happens at the locations that are not part of your training data implicitly, right? And of course, the whole thing is a neural network. So how does that adversarial thing work? We will see that in a minute. It turns out that that GANs are made of two competing networks, adversaries that are to outdo one another. So just a bit of history. It was introduced originally in 2014. The GAN framework has been around for a long time. In fact, when Ian Goodfellow liked to present these GANs in conferences, you had other scientists from Germany coming and arguing with him that they had already invented it a decade ago. And it could get kind of nasty. But anyways, the concept that you want to have set up two networks that are trying to, or two models which are trying to outdo one another has been around. It was applied specifically for the problem to train neural networks better, first in 2014. The goal is to model P of X, the distribution of the training data, so that you can generate samples from it. But the way you do it, you use a pair of models which are acting as adversaries. The first is the generator, which actually generates data. And the second is a discriminator that evaluates it. Now, to give you an idea, how does this work? Let's go back over here. For this model, I'm saying that if I'm training a generative model, maybe Z is drawn from some Gaussian, right? And then these samples that are drawn are put through some network. And this is what your sample values are. And then we saw that we can train this distribution to maximize the likelihood of training data. And the only thing you refer to when you're training a VAEs are the training data. You're not referring to anything else, right? But then I want to ask the question, does this guy actually generate faces which are not the training data? So if that were the case, and if I used it to evaluate this model, How would you do it? How would you know that it's doing the right job if you're being naive about it? What's the simplest thing you could do? Imagine you were the first person training this model. You had this brilliant idea for these variational autoencoders. You trained your model and you said, aha, now I've trained a model that can generate landscape pictures. You want to know how good it is. What would you have done? You're already getting too sophisticated. Is that what you would have done?
Compare it.
You would have drawn random samples from it and eyeballed it, right? Isn't that the most simple thing you would be doing? Don't get too sophisticated, guys. You're going to get tangled up. You don't need to go that far, right? So, and what would you do if you found that, yeah, it gave you a high likelihood on your training data, but then when you generate random samples from it, it looks like Picasso, right? Then what would you do? What loss? It's you, right? What would you do? Yeah. You're sure. You're throwing math at me, right? But just put yourself in the shoes of the person who first wrote that piece of code. What would you be doing? Change the code. You're going to begin mucking around with the parameters, right? You're going to say, what happens if I'm just parameters a little bit? You know, you'd go back, maybe eyeball the parameters, say, if I change this thing a little bit, it looks a little more like a landscape. If I change this other thing a little bit, it looks a little less like a landscape. And you would keep mucking around with it while making sure that it stayed true on the training data itself. Or you'd begin sort of poking around with it till it generated something that was more and more landscapey, right? That's going to be a tedious process. The tedious process, and it's tedious because you are not a differentiable person, right? I cannot differentiate you, and I cannot compute derivatives which tell me which way to modify millions of parameters to fix the model. So instead, we will computationalize you. I'm going to put in a computational version of you, which is going to look at the output of this network and say, yeah, this looks like a landscape. No, this doesn't look like a landscape. That is the discriminator, right? It's a very simple idea. And if the discriminator were you, if it were perfect, yeah, you would be able to, you can sort of use it. So what is the discriminator? The discriminator is able to say if something looks like a landscape or not. But if I'm computationalizing you, what is the first thing I would do? I would need to actually have to, I'd actually have to train the discriminator, would I, right? Right? You need to know what a landscape looks like. So how would you train this discriminator? Okay, fake or not fake, right? You can give it landscape pictures and you can say, okay, fake. What kind of fakes? What that's it. What do you say, Michael? You can put in, I can put in Picasso paintings. I just, but I should have used that picture of Picasso. I mean, the fantastic painting of Picasso painting his girlfriend. And I found it on the web yesterday. I was wondering whether I should have it in my slides. It was rude because it looked like an octopus. But anyway, we stared at it hard and long, and then realized that, those were not octopus limbs. They were actually hers. Anyway, but the point is, what are the fakes? Is that generator going to be knowing to distinguish between landscape and Picassos? Does that help this problem? Yes or no? It does? It doesn't, because your classifier knows to distinguish between landscape and Picassos, but the generator is not generating Picassos, is it? Right? So how would you want to train the discriminator? What kind of discriminator would you want? Any discriminator, or something that's actually able to distinguish between what the generator generates and real landscapes? Which of the two would you prefer? You're going to choose the latter, right? Something that can actually distinguish between what the generator generates and the landscape. Does that mean now I can just have a fixed discriminator? Because as the generator gets better, the discriminator also has to adapt to what the generator is currently doing, right? So The whole idea is very simple, but then here's the problem. The evaluator that you've got, which is now a function by itself, replacing you, has to adapt continuously to what the generator can do. And so here are the two aspects of the model. One is the generator and one is the discriminator. So the generator's job is to produce realistic looking X from some latent variable Z. Yeah.
You do some sort of positive sampling so that you don't just get this, smart aleck discriminator that says, well, you're always feeding me false, so I'm just going to say false.
Yeah, he says yes, right? See the real data X in the picture? Yes. When you're training the discriminator, you need to train the discriminator to. So you're going to give it, it's not pairs, it's just a standard discriminator. When you trained your MLP, what did you do? You gave it positive and negative instances, that's it. It's not comparing anything, it's just a standard discriminator. Sometimes you give it, if you give it a single instance, it tells you whether it's a landscape or not. Yeah.
So the labels for all generated data is going to be false.
Yes.
Even if it's like, if it happened to output a nice looking landscape at one time.
So, yeah, so how confident would the discriminator be in that case?
Oh, okay.
Right. So you sort of said, you answered, you can come over here and take over the rest of the lecture, honestly, because you've answered most of it. Yeah.
Once we train the generator, we also have trained the discriminator.
It's specific to that generator, but then so there's a little more to the finesse, right? The generator generates realistic looking X from the latent variable Z because we're using this reparameterization trick. And now Z can be sampled like a standard Gaussian, put through the generator to generate new samples. Our goal, as I mentioned earlier, is the distribution of the generated samples matches the distribution of real data from the class as closely as possible. So if I'm trying to generate landscapes, that PG, the G and underscore, the subscript G mentions indicates that it's from the generator, right? The distribution of data generated by the generator when you feed it Gaussian samples. So let's be very clear, or whatever you chose as the seed distribution, right? So that PG of G, which is what I had on the formula earlier, that thing must really look like the distribution of landscapes or faces or whatever it is you're trying to generate. The discriminator is trained to tell the difference between real and synthetic data. So basically it's replacing you. You are very smart. If you were, if your thought processes could be differentiated at lightning speed, I could plug you into the entire process because you guys know what is a landscape and what is not. But computationally speaking, you have a discriminator which says the output of the classifier, is this an authentic landscape or is it something that's synthetic that has been generated by this one guy and not by Pablo Picasso, right? So that is specifically the data generated by the generator. Now, suppose I have a perfect discriminator, so how perfect is a perfect classifier 100% accurate? Then, how accurate is it? How do you define a perfect classifier? Can anybody tell me? So anybody, how many of you know what a Bayes error rate is? Have you heard of Bayesian classification? That's a number. So here is what happens, right? If I'm trying to distinguish between two classes, then let's say I'm looking at the distribution of, say, heights for men and women, and I'm using heights as my feature for generating, for deciding if a person is a male or a female, right? Then if I plot the distribution of heights for males and females, for males, it's probably looking something like this. You get tall people, you get short people, you get the entire range, right? For females, you're going to get a distribution. Is it going to be the same thing? No, it's going to be, the means, you're going to get something like this, right? Okay. And so now, if a person is tall, is it always a male? No, right? If a person's short, is it always a female? Right? You must have found this. So if I'm using height as a condition to decide whether a person is male or female, what is the threshold I would use to decide if someone is male or female? Exactly where they cross, right? Because if I move the threshold out here, so what happens if I use this threshold? This portion of this distribution and this portion of this distribution represent data that are going to be misclassified. Correct? If I wiggle the boundary a little to either side, if I wiggle the boundary out here, then this portion of this and this portion of this guy are going to be misclassified, right? The error is going to increase. So specifically, your decision is going to be where P of y1 given x equals P of y2 given x, right? Your perfect classifier is never perfect. It just means there is no other classifier that can do a better job on average, to be very, very clear, right? So now suppose I have the perfect classifier over here. And my discriminator manages to produce my generator manages to produce an instance which fools the perfect classifier. So clearly, in this case, what would I do to fool the perfect classifier? I'm going to generate data out here, right? For this class, or out here for this class, right? So if my perfect generator is able to fool my perfect classifier, then what has it done? It has produced something that looks more like the target class than like nonsense, right? So you want the generator to learn to fool the discriminator. Basically produce something on the other side. You want the generator to fool not just any discriminator. If I'm flipping a coin, it's a totally useless discriminator, right? You want the generator to fool the perfect discriminator for the current setting, right? Your generator has some way of generating data. You have a discriminator that can make distinctions, and for any given sample, you wanted to try to fool the discriminator. Now, how would you train the discriminator? You're going to start off with training samples of real and synthetic faces. So you initialize your generator, you generate a bunch of stuff. Then I'm also going to give it a bunch of real faces. And then using that, I'm going to train my discriminator, just your standard criterion, right? And then you train it to minimize the classification loss. And then the generator. So now if I have a discriminator, the discriminator is fully differentiable. For any given training instance, what can I do? So here, when I modify the parameters of the generator, what happens? When I modify the parameters of the generator, the samples are not changing. What is changing is the entire distribution, right? So when I modify the parameters of the generator, we saw this, I just explained this even when we were talking about VAEs, we are sort of modifying the distribution that the data that the generator can produce, right? And so I want to sort of modify the parameters of the generator so that a discriminator is going to currently have some specific boundary. So what would happen is maybe initially you have these data, right? Your perfect discriminator for these data are going to learn this boundary, right? Now, what do you want to do? I want to sample data, generate data, but from I want to generate data. The generator must generate data which fools the discriminator. So I want the generator to move this entire distribution towards the other side of the boundary, right? And so the generator tries to move forward and push its data on the other side of the boundary. And what will the discriminator do? It's going to try to take a step back and pull the boundary backwards. There's a limit, right? And where is the limit? This is the distribution of real data. This is never going to change, right? So maybe you start off with this distribution. You train a discriminator, it gives you this boundary, right? Then you update your generator and you move it such that it moves further into this point. But then the discriminator is going to adjust itself and give you this boundary, right? Then you update the generator again and you move it further to the right. The discriminator is going to adjust itself and learn the new boundary. In the limit, what will happen? In the limit, this guy is going to come and sit right on top of this fellow, right? and the discriminator becomes, what does it become? It becomes perfectly random, right? It's a perfect discriminator, yet it's perfectly random. That making sense? So it's just how the whole thing works. So the generator is trained to make the discriminator make errors. So the generator is trained to push the data on the other side of the boundary such that the discriminator makes mistakes. The discriminator is trained to reduce the discriminator's error. So basically the generator is trying to push the data on the other side of the boundary. The discriminator is pulling the boundary back. That making sense to everybody, right? It's so if I think of the discriminator as some function d of x, for real data, the desired output of the discriminator is d of x equals 1. That's basically the discriminator is saying it's real with probability 1. For synthetic data, ideally the discriminator must say d of x equals 0, right? And so you basically, the log probability of assigned to real data as computed by the discriminator is going to be 0, right? Or log of d of x. For synthetic data, I can think of it as what is the probability that the discriminator is assigning to this instance that it is synthetic. D of x is the probability of real, right? So the probability of synthetic, or g of x in this case, that's what I'm calling it, d of x. Okay, so the probability that it's synthetic is 1 minus d of x, right? And so the log probability of a synthetic instance being synthetic is log of 1 minus d of x. And x is basically, or I'm not even sure, this should be d of g of z, right? Because x is something that has been produced by the generator, right? So here is the original GAN formulation that was originally given back in 2014, and we haven't really changed from this. This is the basic idea. Here's what we want to do. This discriminator is going to try to maximize the log probability that it assigns to real data and minimize the log probability that it assigns to synthetic data, right? Or alternately, it's going to try to maximize log of d of x. It's also going to try to maximize log of 1 minus b of g of z. So the first term is computed on real data. This guy, I'm giving it a collection of real and synthetic samples. So it says maximize the probability of, maximize the output d of x for real data. And for synthetic data that's coming from the generator, make d of x as close to 0 as possible, which is the equivalent of saying make 1 minus d of x as close to 1 as possible, right? Yeah. You're going to have to alternate, right? So does everybody understand this loss function from the discriminator's perspective? Anybody who doesn't get this, right? This makes sense to everybody, right? So what
Can
is
you
the
repeat
generator
that
trying
again,
to do?
please?
The generator is trying to fool the discriminator. The generator is trying to make this as low as possible. So you're simultaneously you're training discriminator to maximize this guy. You're trying to train the generator to fool this guy. So minimizing this with respect to G. Making sense? Right, yeah. You can write it in any order, right? The point is, it's a so actually that's a good question. It's a good. So suppose I initialize my model. What is the first thing you want to do? I initialize my generator and I initialize my discriminator randomly, right? What is the first thing you want to do? Do you want to maximize the ability of a discriminator to fool a random generator? Do you want to maximize the ability of your generator to fool a random discriminator? Or do you want to maximize the ability of the discriminator to distinguish the output of a random generator? The first thing you want to do is learn to discriminate, right? That make sense? Right. So now you see the order. You want to do the discrimination first, and when the discriminator is, firstly, the discriminator draws the boundary, then the generator tries to push the data beyond the boundary. Right? So
Max that the loss function of both the generator and
simultaneously, yes. Right? So again, the point is I have these distributions initially, these guys, and the first thing you would want to do is to learn this boundary. That's the D, the min or max with respect to D, right? And then the generator is going to try to push the blue guy past this line once this boundary is learned. So the first thing you want to do is to learn the discriminator, right? Pardon me? So yeah, all right. This is just a way of representing it. What data did you compute this term on? The first term. Real data or synthetic data? Real data. What data did you compute the second one on? So basically, you're taking the expectation over lots of real data for the first term and the expectation over all lots of synthetic data on the second term. Make sense? Okay. So, and where the optimal thing is a base classifier, right? So what is the optimal base classifier for an base classifier? Again, for an optimal base classifier, you want what is the probability over here? So suppose I have an optimal base classifier. What is the probability that the base classifier assigns to any particular class? That is simply going to give me, assuming that I give you lots and lots of real data and lots of synthetic data, same equal numbers, right? Then what is the probability for any given data instance what is the a posteriori probability that you're going to assign to any specific class? So the a posteriori probability that you're going to assign to any specific class is, P of y given x is going to be P of x comma y divide P of x comma y over y. You're dividing by P of x. So this y only takes two values. Over there is going to give you the probability that is, so I can write this way as P of x comma y1 plus P of x comma y2, right? This is the base probability, standard base probability. You agree with me? Right, and I can also write P of x y is going to be P of x, it's going to, how do I do this? It's going to be P of y1, y given x times P of x. And if I assume that the probability of any specific instance is the same in both the numerator and the denominator, these things will cancel out. So if so the point is, if the data, you're assuming that the data you're providing to the discriminator are in equal numbers for real and synthetic data, then the posterior probability that is going to compute for the target class is going to be the simple ratio. The score assigned, the probability of the data under so if I'm given some instance, and I don't know if this instance is synthetic or real, then the posterior probability that this is real is the probability of the data under the real distribution divided by the sum of the probability of the data under under synthetic real distribution. So I think I have this written wrong. This should be let me write this right. P of y given x equals P of xy y1, let's say y1, P of y1 times P of plus P of xy2, right? Which is going to be P of x given y1 times P of y1 divided by P of x given y2, P of y2 plus P of x given y1, P of y1. So what is this? What is this term? This is the probability of the data under the distribution of real data. This is the probability of the data. This is the same thing over here. This is the probability of the data under the distribution of synthetic data. And if I'm providing equal quantities of real and synthetic data, these values are all the same, they will cancel out. Assuming that when I train the discriminator, I provide as many real instances as synthetic instances. So the ideal discriminator is just this little ratio, right? And so if under the ideal condition, suppose I say that I'm using the ideal discriminator, and the ideal discriminator is simply computing this little formula over here of the probability assigned to the instance under, or the probability of the instance under the real distribution of real data divided by the sum of the probabilities under real and synthetic distributions. Then let me just plug that into the formula. Assume that I have an ideal discriminator, right? If I'm assuming if I have an ideal discriminator, then I can write for d of x over here just this term, px of x divided by px of x plus pd of x, right? Pd of x is just the distribution of synthetic data. Okay? And similarly over here, it should have been g, sorry, okay, pg of x. This is going to be 1 minus d of x, which gives you pg of x divided by pg of x plus px of x. Right? So everybody with me so far? Just a little bit of math, okay? So what is this guy? If I look at, there's a log, right? There should have been, I'm missing logs in both these cases. I'm sorry, I'm missing a whole bunch of things. What was the point of this? If you actually look at what the generator is doing, assuming you have a perfect discriminator. So skip the bogus math on my slides for now. Take a look. What does the generator do when you have an ideal discriminator? For an ideal discriminator, yeah. Okay. I think it's my motion, right? I guess. That better? Yeah, sorry. So the ideal discriminator is going to be d of x is p, let me call this real of x divided by p real of x plus p generated of x. This is what the ideal discriminator is going to be, okay? Now hold that thought. When I train a classifier, typically, what am I training the data? How am I training the classifier? If I'm using cross entropy loss, forget this setting. If I'm using cross entropy loss, what am I training the classifier to do? I'm providing lots and lots of examples of real data, right? And then I'm giving you lots and lots of examples of real data, and then there's the probability that the data assigns to the training, to the classes, that the model assigns to the classes, right? And so typically what you will be doing is you will be minimizing the KL divergence between this guy, right? You're minimizing the KL divergence between P of y given x given by the model and P of y given x, which is the ground truth. This is what we do, right? And the way we did it was the expectation over x, P of, this is sum over x, y given x, log of, or sum over y, log of P of P real, P model of y given x. So this was the KL divergence that we actually minimized when you trained the model, which is why you said, you know, I'm just going to be maximizing the log probability assigned to the true class, because the probability for any given instance, you assigned a probability of 1 to the true class and 0 for all the remaining classes. But the thing that you were trying to minimize was the KL divergence, right? This is really just a probability distribution. This is a metric that simply computes the divergence between two distributions. Even though we wrote it in this form, what is the KL divergence? The KL divergence computed over lots of data basically says what is the expected log likelihood of the data that you have seen under some distribution. It's comparing two distributions. And we are trying to train the model such that the divergence between the two distributions is minimized. That's what we normally do. And it has specific form. What is this guy doing over here? If I actually just write it out, it turns out that this whole thing also looks like a divergence. So the KL divergence is not symmetric. The divergence between PM and PR is not the same as the divergence between PR and PM, right? Because one of the terms appears outside the log, the other term appears inside the log. So asymmetric divergence metrics are always bad. We just use it because it's very convenient. Suppose I asked you to make it symmetric, what would you do? So we find that the KL of the real versus the model is not equal to the KL of model versus the real, right? So it's not symmetric. If I try to make it symmetric, what would you do? You would add the two, right? If you add the two here, is still there's always a problem. Why? If you look at the term, there is a log, right? I've forgotten to write the log there, but there's a log. Now, in this case, there are going to be instances which you see in training but not in test. So the probability is going to be under the real data. So the probability given by the model may be 0 to it, right? Or in the training data, you never say it, so you might assume that that log probability is 0. So when you look at it symmetrically, you're going to end up with log probabilities in one or the other terms. You may have situations where the model assigns a non-zero probability to something, but you never see it in data. So in that, you're going to get some term times log of 0, right? You have other situations where it occurs in real life, but the model assigns a 0 probability to it. Then too, you're going to get some terms times log of 0. So the scale divergence is a really nasty metric. What happens is that you're likely to end up with log of zeros. It makes it very unstable. If you look at this term over here, so there's an alternate way of looking at it. If I've got probability P1, distribution P1, and probability distribution P2, then what I can do is compute P hat, which is P1 plus P2 over 2, which is the average of the two probability distributions. Okay? And then when I do this, the only case under which this is going to be 0 is if both are 0, right? And now my divergence is going to be P1 log P hat plus P2 log P hat. This is called the Jensen-Shannon divergence. It has the nice property that you never get a log of 0. When you get a log of 0, it means both P1 and P2 are 0. 0 log 0 is going to be 0 anyway. It doesn't really matter. But you're not going to get log of 0 issues under other conditions. And it turns out that when you actually train the GAN, when your discriminator is perfect, what you're really doing is minimizing the Jensen-Shannon divergence between the distribution of real data and distribution of synthetic data. So although we write this formally out, if you look through the arithmetic, it turns out that the GAN optimization criterion is doing something that you're very familiar with. Now, if I wanted to train a discrete generator, what is the correct thing to be doing? So how does a GAN how does a GAN differ from a VAE? When I had a VAE, I was trying to minimize the KL divergence between the distribution of real data and the distribution generated by the generator, right? We were using cross entropy loss. A GAN is minimizing if at each point you train the best possible discriminator. This is all conditioned on training the best possible discriminator at each time. A GAN minimizes the Jensen-Shannon divergence between the distribution modeled by the generator and the real distribution of data, or distribution of real data. So the two are actually basically the same framework. What has really changed between VAEs and GANs is the loss function that you're using. The loss function in the case of VAEs is the cross entropy loss, which has all kinds of problems as we saw. whereas the GAN actually minimizes the much nicer objective function, which is the Jensen-Shannon divergence. But in order to be able to minimize this Jensen-Shannon divergence at each point, you are required to train the optimal discriminator. Otherwise, we don't really know what divergence it's minimizing, right? I mean, there was a little bit of math over here, but did that make sense to all of you guys, right? If it turns up on the quiz, you will be able to answer this, right? No, okay. The GAN quiz is going to be a regular quiz. It's not an easy one. There will be 30 questions. You won't see it in the second or third attempts. So just be very sure. Any questions over here? Did this make sense, guys? So this is the key difference between the AEs and GANs. That's it, okay? So the Jensen-Shannon divergence is 0.5 times the KL divergence between P and the average of P and Q, plus the KL divergence between Q and the average of P and Q. It's a symmetric variant of the Kullback-Leibler divergence that does not exaggerate instances to which one of the distributions assigns zero probability. And this becomes important, right? So anyway, so the optimal generator, when your discriminator has been, yeah. So, okay, so here's what we were doing. This is when we were trying to when we were trying to train a standard model, what were we actually doing? We were trying to compute the KL divergence between. So for each instance, you had a probability over y's, correct? And so you would do summation p real of yi times log of p model of yi over all I, right? This is what you did, correct? And this differed by instance. And so you are actually summing this over all training instances, correct? So if I actually look at this, the limit, this is the expectation over all training data, because the sum over x is like sampling your data, right? This is the expectation over y given x. This is just taking, this is the sum over all y's, right? So I can simply think of this as x comma y of p of y, p real of y given x times log of p model of y given x. This is the objective that your standard training minimizes. That making sense? Right? Everybody with me on this? Right, okay. So what happens over here? We used one hot representations for this guy, right? For any given x, we said there was only one y possible. May not be true, but that was the one we used, which is why this expectation simply ended up being the log of the one true class, right? But then this is not symmetric. This, if I look at it from this perspective, this is really a divergence between the real probabilities and the model probabilities, correct? But the order in which I write these two functions matters. If I could have done it the other way, right? Instead of saying p real times log of p model, I could have said p model times log of p real. Could I not? Why didn't we do that? You're going to end up with a whole bunch of log zeros. You chose the nicer function that you could deal with, right? What happens if, so also it's not symmetric. We like things that are symmetric, right? If I try to make it symmetric, what can happen? I can do divergence of p real p model plus divergence of p model p real. This makes sense? This is a symmetric version of your standard KL divergence. Now you have the problem twice over, right? If the model assigns zero probability to something, you're going to get a log of zero. If something has zero probability in real life, where your model doesn't assign zero probability to it, you're also going to end up with a log of zero. It's a nasty thing to be doing, right? That makes sense? So our solution to this is to say I'm going to average two distributions. The only condition under which this average is going to be 0 is if the data has real zero probability assigned to it by the model and is not possible in real life, right? And then we compute the average, the KL divergence between P and P, the average of P and Q, and Q and the average of P and Q. So this is symmetric, doesn't have the other problems, it's more stable. Does that make sense to everybody? Right. And so basically the generator is minimizing the KL divergence between the Jensen-Shannon divergence between the distributions of real synthetic data. But for that to work, the discriminator has to be perfect. And the discriminator is trying to actually learn to model a Bayesian distribution, Bayesian classifier. So if all goes fine, what would you do? You'd start out by training your discriminator. Then you train. So here's what we said, right? I have some distributions. This is your synthetic data. This is real data. Your optimal Bayesian classifier, optimal generator learns this model. Then your generator shifts this side. Then the next optimal generator discriminator learns this guy. And you keep shifting things. Eventually, there's a stationary point where you have a optimal discriminator, but it's completely unable to distinguish between what the beta generator generates and real data. At that point, you call it a success. You've trained a model that can actually accept real data, right? So if all the generated data exactly match real data, the discriminator obviously outputs 0.5, the probability of real and synthetic data, right? So it cannot distinguish. But then there's another case, right? What if I gave you a random discriminator which always output a 0.5? There's nothing you can do with that discriminator, right? The entire theory only works when your discriminator works properly. So it's also true of a random discriminator. So you have these stationary points where the generator and the discriminator are sort of canceling each other perfectly. Not all of these stationary points are useful stationary points. There's one and only one of them, or a small number of them, that actually represent a valid generator. For the rest of them, it's just garbage. Okay. So, and the stationary points need not be stable, meaning, you can, if you perturb things a little way, things can change when you're training the model. The generator may overshoot some values or oscillate around the optimum. A discriminator with unlimited capacity can, if I have a discriminator which is too big, then it can be too certain about things, right? So the discriminator can end up going back to the same problem we had with the VAEs, in that it can be very specific to the specific set of training samples you provided and be used as everywhere else, right? All of these issues can happen. So you have this min-max optimization. The generator and discriminator need to be trained simultaneously. If the discriminator is undertrained, it begins to act randomly. It's not really teaching the generator, right? If the discriminator is overtrained, it's too fit to the training data. It's not providing any more feedback, right? So you have this balance. So here's how you train it. Step one, you train the discriminator. You initialize everything. Then you train the discriminator using the current generator, which is to say you optimize this guy, but with respect to only D, right? Then step two, once the discriminator has been optimized and hopefully learned the base classification rule, you've plugged that in, and then you train the generator, and then keep iterating this process. In a more realistic situation, you'd be running a few iterations of one and some iterations of the other.
Oh, that was going to be my question. When do you switch from step one to step two?
Ideally, you just let both saturate, but that's going to be suboptimal and inefficient as well. So typically, you run several iterations of trying to optimize the discriminator, then one or a couple of iterations of tuning the generator. You do blocks of those, but then more steps of tuning the discriminator, because having the right discriminator is important, right? So, meaning what would be?
You mentioned suboptimal as well as why would it be suboptimal?
So
First train the discriminator completely, then go to the generator and then.
the loss function is very ugly. So, I make it sound simpler than it is. It turns out that it is actually, you want to sort of wiggle your way to the bottom rather than swing all the way to one side and then swing all the way to the other side. So GANs can produce very crisp results for many problems, but they also have stability issues and are hard to trace. Problems such as mode collapse, standard thing. If let's say there's one perfect face, and the generator somehow manages to always produce this one perfect face regardless of what seed you give it, your discriminator is always going to say, yeah, that's a face, right? Is this a useful generator? It's not. So this is what we call mode collapse. This is a very common phenomenon. There have been a great many variations proposed to improve the stability and outputs of GANs, lab GANs, Wasserstein, C GANs, DC GANs, blah, blah, what have you. We'll cover some of these in the next class. So how do you know if your discriminator is any good? Now, ideally, you want a human being in there evaluating these things. But you can't stick human beings into things and have them evaluate thousands of pictures. At some point, they're going to run out of patience and give you random results. So you want some computational means for it. So what people do is come up with things like the inception score, where they actually use other classifiers to decide if these things are useful or not. We'll learn more about inception scores if you read about it. I won't go into, or maybe we'll cover it. I won't go into it here. So, okay. The inception, but the whole point is this: you want the model to have variety in its output, right? And so what we would like to do is, if I take a generated image and put it through something like a image classifier, then each instance should produce different labels. So let's say I have an image classifier which is ideally classifies between different kinds of faces. Right? Then if your generator is doing a good job, then over a large collection of generated faces, the distribution of the labels that the image classifier produces should have high entropy, right? So at the same time, any individual instance, the confidence should. So they come up with a score, which is a combination of the two. So to compare, VAEs, they minimize the KL divergence between the distribution of synthetic and true data. GANs minimize the Shannon divergence. The VAEs use an encoder to predict latent distributions to optimize the generator. GANs use a discriminator to just optimize the generator. The VAE formulation was much more complicated when we saw it. The GAN thing is trivial to understand, right? On the other hand, when you begin coding it, and when you try to, give me a second. So, when you try to actually have this thing converge, you'll find that your VAE always converges very nicely. Your GAN gives you hell. So, there's a trade-off, right? And VAEs, like I said, they may learn to do all the right thing at the training instances. There's no constraint in the VAE in what happens at other instances. You're depending on hope. GANs are kind of optimized to produce the right thing pretty much everywhere. So GAN images tend to be a lot sharper. So here are some examples. This is the original GAN paper from 2014. They were trying to produce different kinds of images. That's for MNIST digits, faces. I'm not even sure what the blobs below there are. But then with time, here's what has happened. You've gone all the way from the black and white age to high def age over just a few years. 2018, that's a totally imaginary face. That person doesn't exist, right? You can see how fantastic it is. This one, star GAN. Now, we'll actually, hopefully in the next lecture, we'll see how we can use GAN to many things and do things like style transfer and so on. The basic still remains, right? So here, for example, you can make these GAN generators conditional. And you can see how we can actually use it to modify specific things like the gender, the color of the hair, things like that. Or you can start off with data of one kind so for example, you can have a combination where you extract some latent variable from one image and use it to reconstruct the new one and change the domain. Lots of fun stuff. These are all 2018, extremely realistic, right? I mean, which of you wouldn't like to encounter one of these people in public? They don't look scary. They're all very good looking, So, but this is my favorite, produced by Gans. And I'm a foodie. I like food. The picture to the bottom left, I can totally imagine myself eating it. The coffee to the top right, those two make a great combination, right? So the mushrooms, just look at the detail on the mushroom. Or these, this was not drawn by an artist. It was totally randomly generated by a neural network. Now, if you can imagine that, that's something else, right? Or look at this dog. I love the dog. He doesn't exist. So the point is, all of this comes from this very simple formalism that we just saw, or that bubble there is absolutely picture perfect. So all of this comes from this very simple form. The basic idea, just to go back, although we saw a lot of math, is eventually the best judge of whether something that is being generated is valid or not is not some abstract quantification like likelihood. It's maybe yourself, right? Or some computational equivalent of yourself. That's where the discriminant comes in. So the discriminate, being able to discriminate between what is authentic and what is synthetic can be used as a signature to train these models. And that's the basic concept over here. We'll expand more on this in the next lecture. So I'll stop right here. That's the last slide. Any questions? Yes.